Hello, class. Today I'd like to just briefly review Chapter 2, and if we can get to Chapter 3, maybe I'll do that in a separate video. Um, so let's just get right into it. In Chapter 2, we're talking still about descriptive statistics, and one of the first concepts, which is a very important concept, is the frequency distribution. And by the way, I'm using your book here to kind of go through this in a systematic way. But you'll see that there are presentations of very simple tables where they'll have a variable, gender, and then they'll have two attributes of that variable, or another way of saying that would be two ways that that variable would be broken out. And in this case, it's male and female. And so they'll list the variable, and then under that the attributes, male and female, and right across it will list the frequency for each category, each attribute, and then the total, which is represented by the capital letter N, is presented. That's a very simple frequency distribution. If you look in your book and you look at some of the tables, for example, Table 2.2 and Table 2.3, you'll see some good examples of very simple frequency distributions. By the way, you can look in your book, but of course, as you know, your book is contained in MindTap, so you can look at it there as well. Now, again, we're taking large amounts of data and we're describing it. That's what we're doing in the first several chapters of this book. We're engaging in descriptive statistics. So one of the ways that we can describe a large group of numbers would be through a percentage, very simple. Another way would be through a proportion. Another way would be through a ratio. Now keep in mind, by the way, a ratio, a percentage, a proportion, those words represent a statistic. And what I always like to say is that a statistic is a symbolic representation of a large group of numbers, so that the reader doesn't have to look at the large group of numbers. They can look at one statistic and get a good idea about what those numbers are saying. That's really an important concept because that's what statistics really means, especially on the descriptive side. Now, if you look at the discussion on percentages, again, you all have done this in your life, I'm sure, everyday life, but to calculate a percent, you take the frequency of a particular attribute of a variable, you divide it by the total number, and then you multiply that times 100. That's Formula 2.1 in your book. It's pretty self-explanatory. Pay attention to the symbols, the little scripted letter F, and so on. And of course, your author gives you a few examples right below that formula about how to calculate it. And I strongly suggest you do the calculations even though you're reading it, just to prove to yourself that you can do it. Okay, so let's go to Table 2.5 and see what they're talking about there. This is a table. The variable is the major, right? How does the major vary? Well, according to the table, it varies by the attributes being a business major, a natural science major, a social science major, or a humanities major. We have one college, College A, and it tells you how many majors there were for business, natural science, social science, and humanities. Then it gives you the total at the bottom of the column. And College B, the data gives you the same thing. Now, if you're looking at those numbers and you're trying to make a comparison, what your author is trying to impress upon you is that it's difficult to make a comparison unless you convert those numbers into something like a percentage. A percentage standardizes all those numbers to a base of 100 and makes it easier for us to conceptualize what those numbers really mean. He does that in Table 2.6. And you'll see the percentages of majors in each college. By the way, that's important. Why is it important? Because if you look at the N, the total number of students in College A, and the N, the total number of students in College B, N is very different. In College A, there are only 415 students. In College B, there are 9,979 students. Nevertheless, we can still make a comparison about the percentages or the proportion of the majors in each school by standardizing those numbers to a base of 100 and making them into a percentage. Okay, I hope that's clear. That's an important point, by the way. Don't overlook it. If you look at Formula 2.2, you'll see he gives you the formula for a proportion. Well, look, the formula for a proportion is basically the same formula as it is for a percentage. And in fact, when you calculated the percentage, before you got to the percentage, you actually calculated a proportion. A proportion is standardized to a base of the number 1. A percentage is to a base of 100. But to get to the percentage, you had to get first to the proportion, which is the one with the decimal point, right? And we all learned in middle school that we moved that. If our answer was 0.2 and we wanted to convert that to a percent, what do? We move the decimal point 2 places to the right and convert it into a percentage. And if you look at some of the examples that he gives, or your author gives under Formula 2.2, I think it'll be clear. And listen, there's an important point I want to make. In your readings, you'll see applying statistics boxes, one step at a time boxes. Please don't ignore those boxes. We tend, when we read our textbooks, to skip over the boxes. We go, wow, what a short page, there's a lot of boxes. In this particular book, the boxes are excellent. And in fact, if you work through the boxes, you'll learn the material so much better. Even though, for example, in the box entitled Applying Statistics 2.2, you're given an example, and then you can read it and you can see what the answer is. Take out a calculator, take out a piece of paper and a pencil, work through those numbers even though they're given to you, to prove to yourself that you can do it and you understand why. That is so important in this class. It'll really help you to do well. So don't ignore any of the boxes in the book, please. Okay, so if we look now at table 2.7, we have a frequency distribution of ordinal level data. Remember the ordinal level of measurement, what it was, right? Categories that can be rank ordered from low to high. Nominal level of measurement were categories, but they couldn't be ranked. It made no sense to rank them. An example of a nominal level category would be religion. We used that in the last video. And religion was broken down into attributes, for example, Protestant, Catholic, Jewish, other, or whatever you want to use. But it makes no sense to say that one category is higher or lower than another. In ordinal level of measurement, we still have categories, but those categories can be rank ordered. So you'll see in the example in table 2.7, very typically the categories are strongly agree, agree, disagree, strongly disagree. And again, there's a frequency column with the raw number, and there's a percentage column. And keep in mind, for each attribute, for example, strongly agree, the frequency is 350. If you divide 350 by 1,370, you'll get 25.55%. And if you do that same process for each one, that's how you calculate the percentages. Also, keep in mind that your percentage column should total 100 or very close to it. I say very close to it because sometimes rounding off numbers makes it off a little bit. But it should make sense to you that when you add up all the categories, they total 100, which is the total universe of the numbers. So let's continue on. And we're now going to talk about frequency distributions that are involving the level of measurement of a variable at the interval ratio level. So when we did the gender, male and female, that was a level of measurement at the nominal level. When we did strongly agree, disagree, etc., that was a frequency distribution related to ordinal level of measurement. And now we're going to look at interval ratio level of measurement. And remember, interval ratio level of measurement is numerical, has a lot of numerical properties. You can do a lot of arithmetic with it. You can add up the numbers and divide, and it makes sense to do that. It's a very sophisticated level of measurement. Very important that you try to understand that. If you look at table 2.9, the variable is ages, and the attributes of the variable ages would be the individual ages that are listed there. By the way, you can add up those ages and get a mean average, correct? Just like you could for your test scores. It makes sense to do that. That's what I mean when I say that you can do a lot of arithmetic with this level of measurement that you cannot do with the ordinal or the nominal level of measurement. And so again, looking at table 2.10, you'll see that age was grouped. People who were 18 to 19, 20 to 21, 22 to 23, 24 to 25, 26 to 27. And basically what your author is explaining to you is, let's count up the number of people who were 18 to 19. Now that would mean you go through the list and you look at everybody who's 18 and everybody who's 19. 20 to 21, same thing. 20 to 23, 22 to 23, same thing, etc. And then you have a frequency of the group 18 to 19 of 11. The total number is 20, so if you divide 11 by 20, you'll get 55%. And you should do that, as I said, with your calculator for each one. Very important. Now, keep in mind that when we grouped them, 18 to 19, 20 to 21, we created intervals, okay? We didn't list them individually as your author did in table 2.9. We grouped the data, right? We grouped them into an interval, a class interval. Remember also that this level of measurement is continuous, that the attributes, the categories, actually run into each other, as opposed to, as is the case with nominal or ordinal level data, where the categories or the attributes are discrete, where they do not run into each other. Protestant, Catholic, Jewish, they're all separate categories. Male, female, separate categories. Age, however, the distance between ages can be broken down infinitely so that the data run into each other, right? That's an important point. You'll see this now as we look at table 2.11, for example. The class interval that was created for this particular example is trying to show you how you find the midpoint of a particular class interval. So the class interval is 0 to 2, another one 3 to 5. I'm looking at table 2.11 once again. The interval 6 to 8, and 9 to 11. Your author is showing you another column, a midpoint. So for example, between 0 and 2, you add 0 and 2. Those are the endpoints. You divide by 2 and you get 1. For the next interval, you have endpoints of 3 and 5 of that class interval, 3 being the lower limit of the class interval and 5 being the higher. You add those together, you get 8, divide by 2. The midpoint of that is 4. Right? This is important, by the way, because when we want to work with an interval, for example, 0 to 2 or 3 to 5, we don't know how many pieces of data, how many cases had a score of 0, 1, or 2. I'm looking at the first class interval. So we presume that all of the cases in that interval fell at the midpoint. So instead of saying, well, we know that 3 cases were 0, 2 were 1, and so on and so forth, we say that they all were 1, right in the middle between 0 and 2. We're kind of taking an average within that class interval in order to work with the class interval. If you look at the class interval example under table 2.11, the class interval width of 6, the second one, the second example, you have 100 to 105, right? Again, you add them together, divide by 2, and you'll get the numbers in the midpoint column. The midpoints are very important. A couple of other items, by the way, that are important are that when we talk about the class intervals and what we just looked at, they're known as the stated class intervals. So in the table 2.11 again, 0 to 2, 3 to 5, 6 to 8, 9 to 11, they're all stated class intervals. And by the way, if you look at the table 2.11, you'll see 0 to 2, and then the next interval is 3 to 5. It looks like there's a space between the 2 and the 3, right? The 2 is the upper limit of the first interval, the 3 is the lower limit of the next interval. But as we said, with level of measurement at the interval ratio level, there's not supposed to be a space in between each. There's not supposed to be a gap because the data is continuous. It runs into each other. But there's a way to deal with that, and we're going to talk about that now. So that's the stated class limits, and it looks like there's a gap. Now, if you look at the discussion in your book under the section entitled Real Limits, you'll see that we did something to the intervals. The stated limit of 18 to 19 became 17.5 and 19.5. The stated limit of 20 to 21 became 19.5 and 21.5. What did we do? Well, if you look at the stated limits of 18 to 19 and the next one 20 to 21, you'll see what I was just talking about. Looks like there's a gap between the 19 and the 20. So what do? That gap, let's find out how big that gap is. Well, between 19 and 20, the gap is 1. Okay? If we take that 1 and divide it in half, we get 0.5. And what your author is explaining to you in this section is you take that 0.1, you take the number 1, you divide it by 2, you get 0.5. You take the 0.5, subtract it from the lower limit, and add it to the upper limit, and that creates real limits. And if you look at the real limits, right, you'll see that there's no gap between the class intervals anymore. The data touch, indicating that the data is continuous, as we've been saying all along. There are some excellent problems at the end of the chapter 2.12 is an example of an excellent problem that you could do to work through this. And by the way, that's also really important. And if you haven't noticed this already, your author provides examples at the end of each chapter. He provides answers to the odd-numbered the odd-numbered problems. So as you're working through these, you'll be able to see if you got it right or you got it wrong. There's no way you can do statistics unless you're hands-on, unless you actually work through it. You don't get to understand statistics just by reading the textbook, okay? And remember those boxes. They're really, every box in this book, one step at a time, applying statistics, they're all really, really important. Okay, so moving on again, we're creating frequency tables again in order to give the reader an idea about what a large number of data says without having to look at the data and get dizzy, right? We're providing frequency distributions, percentages, proportions, ratios, etc. Well, if you look in your book, you'll see that your author talks to you a little bit about how to build cumulative frequency tables and cumulative percentage columns. I'm not going to go into that too much here because I think it's redundant to what we just said. However, it's very important, and I think it's self-explanatory. Please read it. Try to do some of the problems. If you have any questions about it, of course, you can always get in touch with me by phone, and we can try to work it out. Okay, so that's it for Chapter 2. I'll see if I can get a quick video going for Chapter 3 for you. Okay?